Swayam Prabha. Digital India. Educated India.
Hello and welcome to the Applied Accelerated Artificial Intelligence course. I am Satyajit Das, so I'll be handling the introduction to AI systems hardware and system software, and I'll be taking some of the SDKs with PyTorch and TensorFlow. And yeah, so that's about it, and let's get started. So these are the contents of today's lecture. So basically, we will start with the introduction. We will see some applications of AI in modern days, just to get motivated in the beginning, and then we will talk about the computing systems from the perspective of AI. So from the perspective of running at artificial intelligence benchmarks, what are the modern systems available and how they can scale, or how we can use them, and what are the shortfalls that are there, and how we can minimize the gap between the requirements and already available systems. So we will talk about those, and of course we will talk about some of the computing engines. We might not be covering all the computing engines that are available nowadays, but of course we will try to cover some of these and to see what are the things available nowadays. So let's see one application as Amazon Go. So basically this Amazon Go provides you the flexibility to have seamless shopping experience. So you go into one shop and you just take your things and you just get out of the shop, and your transaction will be automatically credited, and you will have this seamless shopping experience. A lot of AI is applied here. We will talk about what kind of algorithms or benchmarks that are being used. Another application is from this retail clothing scenario. So you go into one store and you, without any contact, you can just try out the clothing for your shapes and sizes that is available. So as you can see, you can just stand in front of the mirror and you can try out several clothes depending on your requirements and likings, and you can try it out, and you can have bought them as you go. So without even going into the trial rooms, you can have this seamless experience. Again, another application, of course, is everybody knows nowadays the application of automated cars. So basically, self-driving vehicles. So if you see different applications of computer vision and deep learning, you'll see it is most intense use of artificial intelligence in terms of application nowadays. Self-driving cars. Again, you have AI application in the area of medical imaging and automated operations. So based on the images that are available, you can actually have like which way will be the most efficient and reliable way to go into one tumor that is there inside your brain and inside someone's brain, and it can track that without any invasive measures, right? So these are the applications of AI, and there are numerous applications you have heard of. But the main question is, what is artificial intelligence? And here we have many definitions available, but mostly accepted definition was given by John McCarthy in the year of 2004 in one paper published from IBM, and it says that it is the science and engineering of making intelligent machines, especially intelligent computer programs. So the programs that are intelligent, that are not anymore the rule-based or conventional programming method, right? And it is related to the similar task of using computers to understand human intelligence. Okay, so that is the main purpose of emulating human intelligence into the machines through these computer programs or intelligent computer programs. But AI does not have to confine itself to methods that are biologically observable, of course. This is the generic acceptable definition of artificial intelligence. But broadly, it has evolved vastly from the earlier rule-based approach to solve intelligent problems to learning-based approaches. And these learning-based approaches became very popular with the advancement of new computing systems that are like GPUs and FPGAs and different systems like that. So as I was mentioning that learning-based approaches to solve or to emulate human intelligence into computer programs have been very popular nowadays, and these are mostly widely named as deep learning and machine learning. Of course, we will use them interchangeably, and it is important to understand the nuances between them. Okay, so deep learning is basically comprising of neural networks which has more than 3 layers, okay, 3 or more layers. So it includes the input and output layer, as you can see here. And deep learning automates this learning process by extracting the features from the data available. And that is completely or mostly automated because this does not need the human intervention as much as the classical machine learning needs that intervention of human dependence, right? So that is kind of difference between these two concepts. But again, deep learning is uh, one subset of machine learning, as you can see here, right? And now the most important thing is that what kind of computations or what kind of complexity these benchmarks have. And if you understand that, then it will be very easy to understand what kind of computing systems that we can engage them for, right? So the configurations or if you do not understand the complexity of the algorithm, it will be hard to relate to the computing systems that are underlying or that will be running your benchmarks, right? So all these from all these benchmarks that are available in deep learning that are mostly neural network based benchmarks, but they are evolving day by day, and that is mostly because of different algorithmic innovation. So every year you can see hundreds, thousands of paper being published from the algorithmic innovation point of view in machine learning and deep learning and their applications. Of course, when I say applications, they are not confined to only deep learning or machine learning, but they can be applied to, let's say, natural language processing or text processing, signal processing, or maybe speech processing or whatever, right? But of course, these core benchmarks will be used for different applications, including the computer vision also, that application that we just saw as let's say in self-driving cars or Amazon Go or different other applications. So these algorithm innovations are happening along with the more and more availability of data. And nowadays we have abundance of data, and in terms of learning, the more data you have, intuitively your learning will be better. Okay, so so the amount of compute or computation you need to do to train these algorithms are also getting more or more, because you have more or more data, and you have to compute or you have to process those data into the systems that is available at your disposal, but of course the amount increases and the compute intensity also will increase, right? So now with these factors of advancement of AI, it is necessary to understand the computation complexity of AI algorithms, right? So this paper was published last year in archive preprint, as you can see here. And of course, you will get to learn a lot about these neural network algorithms, with basics and different algorithmic innovations, as well as different systems that are available to process them. This is a good read. So in the reference, I will give a link to this paper. But if you see this graph shows a very uh, summarized way of representing these algorithms in terms of their computational complexity, right? So if you see the x-axis in this graph represents what? The top 5 error. Now, what is top 5 error? Top 5 error is that these algorithms are supposed to learn something, and depending on their learned parameters or whatever they have learned for, so basically the parameters that we call them, or the model itself, they will produce different possibilities for your output. Let's say one classification problem. Okay, so these algorithms that you are seeing here, like efficient net, dense net, race net, and all these different DNN or specifically CNN networks or convolutional neural networks, they are supposed to provide you the classification of one data set called ImageNet. Okay? Now, what kind of possibilities they are producing, whether that represents the true class or not, so that is the measure of the error percentage. And top 5 error is if your guess, top 5 guess of these algorithms lie in that your true class of this particular image or video that you are trying to classify, if they lie on their top 5 guesses, then how much percentage of time they can guess that. So that is the measure of this top 5. So that means if you want to increase the accuracy, so this is basically then the graph showing the accuracy versus the number of operations need to be processed for these benchmarks. And these number of operations you can see in the y-axis as represented as GOPS or giga operations per second. You can see that in many places they are also referred to as gigaflops. So floating point operations also the same as GOPS, because all the computations will be in these benchmarks will be mostly for floating point arithmetic, right? So now you have top 5 error. You want to increase the accuracy of these benchmarks, and you need to also increase the number of computations that you need to do for these benchmarks to get more accurate. Now this blue line you can see here is the accuracy measure, right? It is linear. So if you want to get linear increase in the accuracy, the computations, you can see the involvement of the computations get exponentially increased. Okay? And this is the factor you need to understand before going into implementation of these algorithms that you will see in the subsequent classes, right? So now this is one fact or one takeaway from this slide. You will remember that to increase or to get linear accuracy, you need to increase the computations exponentially, right? Now we will look into the computing systems that are available, and we will try to relate what kind of computing systems will be more suited for this kind of computational density or computational complexity that are being incurred by these AI benchmarks, right? So of course, traditional computing systems, as you know, that we have computation engine, and then we have memory, we have memory system, different levels or hierarchy of memory is there that we'll see in the next slide. And you have the communication unit. Now, if your memory is on chip, then you have on chip interconnect. And if your memory is staying outside, like dynamic memory, like DRAM or your storage system, so these are often housed outside of the chip, and then you need off chip interconnect to get access to these memories, right? And if you see the hierarchy of the entire memory system in the modern computing system, you have the register file at the lowest end, and then you have different levels of caches, and L1, L2, L3, and then you have your main memory, which is your RAM, dynamic RAM, and then you have the swap disk to interchangeably uh, uh, interchange programs between the swap disk and your main memory, depending on the locality or availability of the program, right? And that is mostly automated and uh, controlled by demand paging. So most of these concepts also we will see in the subsequent class in system software. But the most important thing in this slide to look at that the speed of memory accesses. Now, if you see in the register files, the memory access speed is highest. Then you have L1 cache in the range of nanoseconds. Then you have many nanoseconds in L2 cache, then some more nanoseconds in L3 cache, and few hundred nanosecond in your main memory access, so DRAM access. And then you have tens of microseconds to milliseconds in the access of swap memory or swap disk available. Now, in the modern systems, of course, your swap disk is extendable to your remote storage through different gateways that you can increase, and you can have several TBs, even petabytes of swap disks available. But just to look at the local system that you can have, the sizes vary from words to KBs to several MBs in the last level of cache, and then several GBs in your dynamic memory or dynamic RAM, right? Now, why this hierarchy is necessary? Because if you see the L1 level of cache, this gives you a very faster access to the computing unit, because the computations are much more faster, and you need the data available to the computation unit much more faster than the dynamic RAM, because dynamic RAM you can see the access is higher, right? The access time is higher. So the lower level you go, the access time will increase. The performance of access time will increase. That means you will get access in less time. And if you go in the upper level, the performance will degrade. And also, you can see that it can house larger size. Okay, so the sizes also you can see. Now, why this is important? This is important because the computation unit now see that that it has now that illusion of high or several level of memory is giving you like high volume. Okay, so larger space. So this illusion of larger space with very short access time is giving you this hierarchy. Okay, so this is why this hierarchy is important. Now, why it is important from AI computation or AI benchmarks point of view? Because from AI benchmarks, we have seen that we need a lot of data to be accessed for training these benchmarks, right? And when we talk about data, memory is the first thing it will come into mind, right? Because memory is where you will store the data. So what modern systems are doing is that, because if you see that access times will be very low for this L1 level of cache, then you keep it the closest to your computing unit, that your processor or core, and then you keep your L2 cache, then you keep L3 cache, and you can keep your main memory or DRAM and swap disk off chip. Okay, and that is what uh, actually happening nowadays. And as I was mentioning that the benchmarks are bottlenecked by the data access. Okay, AI algorithms are extremely data hungry. If you can see that how much data computation it needs per second, right? You have seen the graph before. So for these memory accesses, another key factor is the energy consumption. So size, the access time that we have seen in the previous slide. Now, from the point of view of energy consumption, this memory hierarchy is also important, because the more energy you will spend accessing memory, the more heat you will generate, and you need more cooling system to employ or deploy to cool your systems, and it is much more cost intensive than generating one system or chip, right? So that is why energy consumption is a key limiter of this data movement, and data movement is itself is energy hungry, because if you see this graph of uh, of the data access energy consumption versus data computation. So basically, these in x-axis you will see that these are the different operations. So of course, AI benchmarks or DNN benchmarks are widely dominated by addition, multiplication, and multiply accumulate. So addition and multiplication operations energy consumption you can see here, and DRAM access and SRAM access. So SRAM is static RAM, which technology is mostly employed in the caches. And for RAMs, your DRAMs, you can see DRAM access and SRAM access. The energy consumption is much higher. And if you go into DRAM, it is even several orders of magnitude higher than the computation itself. And if you just compare with add operation, this DRAM access needs almost 6,400 times of energy to access this DRAM, right? So SRAMs or cache-based memory that are on chip, because they give you very short access time that we have seen in the previous slide. And now you can see here SRAM is also giving you much more energy efficiency in terms of memory accesses, and DRAM is giving you much more energy consumption, right? Now, this is the trend that you can see here. But what needs to be done? So modern memory systems, what they do is that, so they employ the L2 caches, the L1 caches inside the core itself. So in these cores that you are seeing here, core 0, core 1, core 2, core 3. So this is the core that is available. And inside these cores, you have L1 cache. It is not particularly visible here, but L2 cache you can see prominently. L2 cache level cache you can see on chip, and then it has shared L3 level of cache on chip, and DRAM is a kind of off chip, because you need higher memory density, and it needs to deploy much larger space of memory. Okay. Now, if you see from the AI computation point of view, I will just give you one example of how much memory that are deployed inside the chip itself to get larger memory bandwidth for running the AI benchmarks. So this chip or this proposal was published in the year of 2019, and this is Cerebrus wafer scale engine. So basically, this whole chip is basically one wafer itself, and all the other chips that you see are basically separate. In one wafer, you will have several number of chips. But this is a wafer scale engine, and this is one ML compute engine. Basically, it has lot of multiply and accumulate unit stored as or arranged as an array of processing engines. And these have this particular engine has 400,000 of this kind of cores. Okay, And on-chip memory, it has around 18 GB of on-chip memory. And this, if you compare the size of this chip compared to the GPU that are available, so the largest GPU that is available nowadays is NVIDIA's Ampere A100 GPU, and that has around 54.2 billion transistors. And this particular WAC or Seri Plus WAC is having 1.2 trillion of transistors. So you can imagine that how much bigger it is in size, and as well as uh, to accelerate, to accommodate all the computations that needed for different AI benchmarks that you have seen before. It employs 18 GB of on-chip memory, and that gives it 9 petabytes per second memory bandwidth. So 9 petabytes per second data that you can access. Of course, this is full precision data that we are talking about. Now, one next generation of this wafer scale engine was published in 2021, and that has 850,000 cores, and that can deploy 40 GB of on-chip memory and having 20 petabytes per second of memory bandwidth. So you can imagine how much memory it is employing. Okay, so just to have this shorter access time and reduced energy, and so all these things we have seen in the previous slide. But of course, these are very highly specific ML accelerators or ML compute engine or AI engine. We will see much more generalized uh, systems that are available and mainstream devices that are available. Okay. So that brings us to the section where we will talk about these specialized computation engines.